well, again, so if your proof, if your goal is to prove this, again, it doesn't matter how you come up with this proof. If you have proof, then it's all right. So another problem is how to build these rules. Well, when you want to build this proof, normally you start with this, and then you see, okay, I have this application. In order to type this application, I have only one rule here is tapp, one rule for application. And you say, you start with this part below, and then you say, well, what should I have in the upper parts of this fraction to get this proved? And you quickly come up that you will need to have this information. So you just infer, well, this left part of the application should be something like this. Then also you should have something like this. Otherwise it will be impossible to apply this rule. Okay, and then you've got these two parts. Then you immediately see, okay, this is typing rule, and we have it already, but this is not typing rule. Then you look, how should I prove this? How should I type check this expression? All right, then we'll need something like that. So if x is of type bool, and to get this type, we need that x should be of type bool. So it should be of type bool because the result of this function of type bool. Then you come up with this, and when you think, well, how can I prove this? So is there any context in which this x variable has type bool? And you immediately come up with this context. Well, here is it. In this context, it will have this type. Yeah, so you prove backwards. Yeah, right. But in fact, this algorithm is not something which is implemented. So implementation of this type checking algorithm is a little bit different. So if you are doing a paper proof, then you do it like this one. But in general, they have many other things, and they have a little bit different typing rules that are possible to. There is a term syntax directed typing. Syntax directed means when you have some term, then all the time you have only one rule that can be applied at this step. And you just take this rule and see what you need to apply it. So it's actually a very straightforward process for doing this type checking here. But still, this is something. So in GHC Core, everything is explicitly typed. So you will have lots of information already because it comes from the Haskell source code. So everything is typed. Yes, I have questions.
So the impression that I'm getting here is that this process is bidirectional. If you start with a variable and say, oh, I know that this variable is a
yes,
rule,
yeah, well, yeah,
you can conclude a whole bunch of things.
It can be done
there.
like that, yeah.
Or I have this statement and it's claiming these things. If this is true, then this has to be true.
Right.
If that is true, then this has to be true.
Yes.
And you keep climbing that staircase, and if something gets violated, that causes a type error.
Right, but sometimes if you choose wrong order for doing things,
right,
maybe sometimes you can have too big space of possible things. So it's very difficult to explore all of them. So it's actually, you have the same thing in logic. If you are doing logic, then they have the same thing to prove if it is true or false. So the same things. All these type derivation things comes from proving things in logic, actually.
Right.
And they have this backward and forward proofs, and
this is reestablishing that the Courier-Howard isomorphism is true. But I remember taking a Principles of Logic class, and one of the things we would have to do is, okay, you have this set of expressions. You can pull this thing out, this statement, and assert that's true out of an AND statement.
Mm-hmm, right.
If you know that you have this OR statement and one of them is false, the other one has to be true. And then you can build up other statements assembling that.
This algorithm depends on the system of logic that you have. If you have simple Boolean algebra, then it's as simple as you said.
Yes.
If you have quantifiers like existence and for all quantity, then it's a little bit different.
Right, that makes it hairier.
Yeah. So in this case, and here, so we don't have quantifiers here. So it's rather simple.
Right.
But then it becomes more and more difficult to do
Well, of
things
course,
like
the more
that.
expressive it gets,
Yes, right. And sometimes it's impossible to have such algorithms actually. So sometimes it will be undecidable task to assign types like this. All right. So let's go back to this safety. So we need that in order to get a good type system, where this good or safe means progress means that if you have correctly typed term, then you can evaluate it to something. So you will not stack somewhere, just you will not stop without actually getting a result. So if it is type checked, then you will get a result eventually. That's a progress property. It's a rather good property. So you are guaranteed to get a result finally. Then another property, preservation, means if you have type checked term, then your result will always be type checked. So you cannot lose this correctly typed property somewhere along the evaluation. So if you had 2 plus 3 and this expression is typed as a natural number, then the result is doomed to be natural number. So you will get 5 eventually and it will be natural number. So that's preservation. So first, if you have 2 plus 3 and it is correctly typed, then you are guaranteed that you can evaluate it to something. That's progress. And you are also guaranteed that it will be evaluated to the value of type natural to a natural number. So that's properties that your type system gives you. Yeah, question.
From understanding the progress, will you be a partially evaluated function? When do you have a type that can be further evaluated?
Well, before you do evaluation, you've type checked everything.
It's a term, not a type.
So partially typed function, it will be partial. Well, you should fully type check it. So everything will be type checked before you start evaluation. And in this case, you will have these properties. So partially evaluated means, well, you just in the middle of evaluating it. You've evaluated one first argument, then second, and then.
Okay, so a term whose type can be further evaluated, that's not a partially evaluated function. That's a different thing.
Yes, I think so.
So I still don't really understand in what case you would have a term whose type can be further evaluated.
Not type, but the value can be evaluated, not type.
Oh, the value. Okay.
Value, not type, yeah. So you have a term, it has some type. This type will not change during evaluation due to the preservation.
So then like a function application.
Yeah, for example, yeah, right, exactly.
You haven't evaluated it yet necessarily.
Yes, but it will have this type, the same type. Eventually. Yes, so sorry.
Would a counterexample be if I had a term which I couldn't evaluate further because none of the rules we had before triggered anymore?
So this basically means that you will not be able to type check it in this type system.
Exactly, but assume I had a type checked already, but we had some evaluation rules before. These do not apply anymore. We had no evaluation rules for typed calculus so far, so I can't go with this example.
Well, again, so if this expression cannot be evaluated, then it can be a value.
I'm searching an example for one of these.
Well, you want to break simply type lambda calculus. It's about 100. Yes, there are no errors in there.
And I was talking about there are many type systems out there which are not guaranteed to follow these properties.
Right.
And I was mentally searching for a good example, counterexample one.
I have one, actually. So, many years ago, I was working in VB.NET,
and yeah, I know. This is where I go. VB.net will happily compile something that says like number plus operator string. It says, okay, yeah, that's fine. When it runs, it says, I'm sorry, you cannot add these two things. They're the wrong type.
So we can talk about
Right.
You know, unfortunately, I will show example in Haskell. So about something like that.
Oh, really?
Yes.
Ooh, man.
So that means basically that's a bug in type system. So if your type system has a bug, then well, you can see everything right there. So we'll see that later. All right. So these basic two properties, and every type system, every extension of this simply typed lambda calculus, which we'll use in Haskell, they will have these properties. I will talk about them again and again. So progress and preservation. We have them in every good type system. Yes.
Does the preservation mean that I can't have a function that takes in a number and spits out a string or a boolean? Can I change the type in the function?
Well, no. So if you have a type for this function, then you cannot change it. So if it's a function over naturals, then it will always be over naturals. So it can be the case that the same function has different type.
I think
that
the main thing is correctly typed, right? If your function
correctly typed,
goes
exactly.
to naturals, it can't produce it.
Right.
I think it makes sense to me that if you have an A to B, you give it an A, you can't get a C out of it.
Right.
Oh, okay, all right.
Right.
Yeah.
So I can
Yeah.
I can set up a function that says I take in a number and I return true if it's 5.
Yeah.
But then I can't say I return
7.
right. Okay.
Right.
That makes
So
sense.
it's 5
Yes.
and 7.
And just to be clear, in order to write a type-correct program, I don't have to type check it. So the construction of the type calculus. So every correct term that follows the construction rules is correctly typed.
Right.
So in order, what you mentioned, your non-type check program wouldn't be a program at all.
Yes.
Without type
Yeah.
check,
Yeah.
so
Yeah.
you wouldn't get even. But I didn't mention that my program would be of the type 100. The type check provides the
Right.
proof of it. That's true, but I was implying some language which would allow us to construct such things. Okay, yeah, probably comes to mind.
Yeah. So in general, so we have when we have type system, we have not only syntax, but we also have typing rules. So technically, using this syntax, we can write many expressions in this language, but some of them will not be type checked, and in fact, most of them will not be type checked. So every type system with its typing rules just limit you with something. So it's really a limitation which gives you these properties. So that's why we use type system in every language. So limit ourselves with something, but get some properties of this limitation. There are other properties of typing relations. I will not talk more about them, but you can find all this stuff in types and programming language book. So there are so-called inversion lemmas, which are very good for finding proofs actually. So if you have this fraction with a typing rule, then you can go from backward direction and forward direction, and these inversion lemmas are about like that. So there is a property of simply typed lambda calculus that every type is uniquely identified. So it's impossible to have an expression with two different types here. There are also canonical forms. For example, this is canonical form for number 3. 3 is it? Yeah. It's 3. So technically, you can write something like suck, pred, suck, then again suck, and it will be 3, 2. Again 3, but it will not be canonical form here. Then there are properties of substitution. When you want to substitute variable, some expression substituted with something. There are other properties about context. For example, you can add some variables to the context, or you can change order of elements in the context, and it doesn't change everything, anything. Then normalization means termination here. So simply typed lambda calculus has this property of normalization, and that means that if you have correctly typed term in simply typed lambda calculus, then its evaluation will stop eventually. It's impossible to have loops here, indefinite loops. So if you know in lambda calculus, you can use such things like some computation cannot stop there. So you have indefinite loops. You can loop forever. It's impossible in simply typed lambda calculus. There are several styles for this lambda calculus. Sometimes you are not forced to specify types of variable in lambda abstractions. Sometimes you have to use it, and there are slightly different properties for this. It's like dialects of simply typed lambda calculus. I'm not going to talk about that. So there are many properties which are proved about lambda calculus. And then when you have correctly typed term, our eventual goal is to come up with a result. So we want to evaluate it. But as I told you already, when you evaluate something, you are not using types. And that means that you can erase those types. And we can come up with something like that. This function erase is just turning your simply typed lambda calculus term into untyped lambda calculus. So technically, the only thing it is doing is just removing this colon T1 part. So you see, it was lambda abstraction, and now it's again lambda abstraction, but without this typing information. So you just erase all type information from the term, and then you have untyped lambda calculus. So, and then you can evaluate it without bothering about types at all. Now, of course, you need this property. It should not depend on the order. You can evaluate it without erasing, and you can get some result, or you can erase first and then evaluate this term using untyped lambda calculus rule, but then you should get the same result. So this is very important property. So you can do it whenever you like. You can erase types in the very beginning of the computation or in the very end of it, and it should be the same. So it's again another property of type system. And this erasing means a lot, actually. As we'll see further, sometimes and in fact, we'd like to erase as much as possible. Because when we erase something, we have less things to evaluate on runtime. So our goal is to make evaluation as performant as possible. So when we write programs, we want them to run fast. So we prefer to do more job during compilation to get some efficient code on the runtime. So that's why this erasing is good. So we want to erase as much as possible. All right, so there is a set of examples for this simply typed lambda calculus too. And in fact, you can follow them. So just several expressions in simply typed lambda calculus, again with the same history. They were implemented first in ML language, then they were translated into Haskell, and there are many expressions that you can play with there. But there is a problem with simply typed lambda calculus. It is not very convenient to use it because remember those property of unique typing. So basically these two functions, they are the same. You see, their body is the same, but they have different types. So it's a functions for applying the same function twice to an argument. So, and even this function, it has the same body. But the only difference between them is difference in types. And it's not very convenient to use for programming language like this one, where you have to duplicate code. So we'd like to have something different. We'd like to have one function and then use it for different types. This is what we called polymorphism in programming. So we won't have that. in our programming languages. Unfortunately, there is no such thing in simply typed lambda calculus. So you have to do it manually for every type that you want to work with. So that's the problem, and this problem surely can be solved with better type system. Yes?
Well, you can use encodings to kind of model polymorphism in the simply typed lambda calculus, or no?
I don't think so.
Okay.
I think that it is impossible there.
You know, like church encodings of data types?
Well, yeah, it is on type,
this
but
is
I
type,
think
got you.
I think it is difficult to model it here with simple type system.
Yeah.
You can have a sum of all the types you're going to use in practice in a program.
Right. Okay, so now we are going to the brilliant piece of theory, which is lambda cube, or Henk Barendrecht lambda cube. Barendrecht is a Dutch scientist, very well known. He's very well known for the book on lambda calculus. Lambda calculus, its theory and semantics. So this lambda cube was his invention. He decided to structure different type systems that were known at that time. So it's not a very old invention, it's 1992. And all these type systems, they were in existence at that time. So, and in fact, I think they were existed since 70s. But Barendrecht was able to build this system of lambda cube in order to I don't know how to say that. So when you have many type systems, it's very difficult to see some correspondence between them. So they have different properties, they look very differently, and when you have no such thing like visualization like this one, then it's very difficult to think about all of them. You just have many facts, and they're very they just don't come up in a system. But then Henk Barendrecht come up with this idea, and you see simply type lambda calculus right here. Here's one. And then there are 3 ways to extend it differently. So one way to extend it, like this one, it's this edge here, is to make your values depends on types. Remember those double not, double bool, double fun functions. We want to make one function double, and its actual value will depend on type which we specify for it. We'll see examples shortly. Or, so this one is just making your values depend on types. So it looks like value, it's just one value, but dependent in dependence with type, it can be different value. So this one is depending types on types. So you want to make functions over types. For example, like in Haskell, we have type integer, and we have type maybe integer. That's an example of this thing, when type maybe integer depends on type integer. It's like a type function, type level function. So this is this part of this lambda cube. And then this part, this edge means depending types on values. There are 3 possible ways in this dependence. First one, again, values depends on types, types depends on types, and this one, types depends on values.
So it's not symmetrical. It depends on which direction
yes.
you go.
Well,
Right?
So
values first and then types. It's like 2 different. You arrive at 2 different spots. I don't know.
Well,
I would think it'd be symmetrical, maybe.
Well,
see what I'm saying?
well, it's not, because there is no values on values dependence here, because depending values on values are just functions. It's not about type systems. So we should have types everywhere here. Yes.
Does this mean Haskell is right now in the top left corner?
Just a second. So this pi actually refers to dependent typing. So these are dependent types when types depends on values. So then you want to come up these to combine these three dependencies. For example, here lambda omega here is you have two properties. You can say that types depends on types and values depends on types. So in this corner. So this corner. In this corner you have all of the systems combined. So you have all the dependencies that can be expressed in this corner. And technically in Haskell, as we'll see, Haskell was for a long time it was here. So it was possible to make functions depending, types depending on types and values depending on types. And now it is currently moving toward this corner. So introducing dependent types means moving along this edge to what we want to acquire finally in 2 or 3 years.
This is a partial order?
Hmm?
This is a partial order.
Yeah, I think so.
Yeah, okay.
Yeah.
Question. When you have types that depend on values and values that depend on types, don't you already have types that depend on types? Or?
Technically, yes. But by the way, this well, it's very interesting picture. But when you try to classify difficult objects within simple framework, it's a little bit unfair in most of cases, actually. So it's a good visualization, but when you are talking about real languages, it's always something like not exactly this, but very close to this. So it's actual type systems are a little bit different. Yes.
So the answer to that is no, because there's like a hierarchy. There's not like there's many different levels of what you mean by type. So you have it's like not like cyclic. You know, it's not just because you have values that depend on types and types that depend on types that you have types that depend on values, because there's like you have to promote something to the right level before you can talk about that.
Well, technically, there is. So if we are talking about theoretical type systems, so if you want good properties, then you really have this hierarchy of types. But in fact, you don't have to have this hierarchy, because type system that is implemented in Haskell is unsound due to the fact that we have recursive computations. So we can write evaluation which doesn't stop in Haskell. And that means that from the type theoretic point of view, this system is unsound. So that's why we don't want to have these very strict properties of type systems there, because we already have unsoundness in this language. So that's why we don't have to think about these types, which depends on types and then different levels of types. Everything has just one level in Haskell. So it's not real type theoretic system. All right, then. But so this is just a good picture. So our goal here is to follow this path. We will look here, and then we will look here, and then we will see how to move here. So this will be our path for the rest of this talk here. So we will follow this lambda cube. So just our path for this workshop. Yes.
Unsound in this context sounds strange to me, because something usually I think is unsound if it's unsafe. It means it fails at some point. If something doesn't terminate.
Yeah, but
it would be bad if it terminates. And
but it's real world. Real world is unsound.
No, but at least automata theory, what causes it's not live if it doesn't terminate. If it
right.
never terminates, that it would call it sound because it's kind of.
Yeah. So unsound. So in theory, when you say unsound is something bad. So sound is something good. Unsound is something bad. But in real world, everything that we are doing is actually unsound, and that's okay.
Wouldn't unsound here mean if it terminates it's wrong, which would be bad?
Yes. But again, so real programming languages, industrial programming languages like Haskell, they don't have to think about that.
Well,
No.
but I want sound, and sound is at least when it starts.
But it's impossible to get this soundness in the real world. Well, because you will work with some database and it will give you the wrong result, and then you can do nothing with your very, very good sound
but
language.
The notion of sound is much too broad. Because
Right, right, yeah.
In a more narrow sense, we have sound because I know if the type checker
Right.
stops, I get something.
Yeah, of course it's about right definition.
So what would be in this context the right terminology there for kind of distinguishing these two cases? Because it's an important distinction.
I don't think that we want to provide very thorough definitions for that, because in this case you have to follow the books, like all of these thousands of pages of books to get to the right place. Well,
if it's intentionally unsound, of course there are bugs in there, but if someone tells me, oh, this is intentionally unsound,
well, again, the basic point where it becomes unsound is the possibility of non-termination. So, for example, if you have programming languages like Idris or Agda, where you can control this non-termination, then you will have theoretically sound language. But if you have non-termination right in the language, then it will be unsound.
To me, it seems like we don't have complete. We have soundness, but not completeness. Usually, I would think, a proof system that might not terminate is incomplete, but it's sound when it kind of gives the results. So it seems that type theory uses different than in logic, and I try to understand.
No,
It's the same as in logic.
it's this.
Contradiction. It's not sound, and by not terminating, you can prove contradiction.
Well, I think that in real life you have to. So you have type theory at some stage of your working with your program, and then you just throw it away because it gives you what it could, and then you just work in real life. So that's it. So and that's why. Well, technically, mathematics is all about that. So in mathematics, you have some properties like. I don't know, some formulas for how to compute square, area for triangle. But then when you apply to the real world, it's not triangle anymore, it's not circle, it's some different figure.
Well,
and then you try to apply it in the wrong situation, but it works. Well,
no. I mean, look at you're plotting the trajectory of a ball. Okay, it's going to follow a parabola, and that's a well-formulated thing that you can just model.
Well, it's not parabola because you have air, you have tension, you have lots of other things. All right, let's not follow this discussion. Let's go back to the lambda calculus, and our next step is system F, or polymorphic lambda calculus, or lambda 2. So it's just one step from the simply typed lambda calculus. So this was invention of Girard and Reynolds, exactly this system F, and I will follow the same approach. So how we can extend lambda calculus in order to get something here. All right, so this is an example of polymorphic function. This is identity function, and in system F, we can write types like that. So this is a type. So for all type X, you can come up with a function from x's to x's. And this is its body. You see it's lambda, big lambda is for abstracting type variables, and small lambda for abstracting value variables. So you have some type X, and for this type X, you have some variable, small x of this type, and then this is the body of this function, just an identity function. You take x and return x again. And when you have this system, you can come up with type application here, and then you get identity function for natural numbers. And in the same way, you can come up with identity function for bool values and for any other types. So system F allows you to do things like that. This is function double. Again, it's just one body. You have one type, which is with big lambda. It's just big lambda just for binding this name x. Nothing more. You have value f, you have value a, and then this is your body. And then you can come up with an instance of this function using type application. So these square brackets here, they are used for providing arguments for these big lambdas. So basically we have two abstractions, one for types, another for values, and we have two applications, one for types, another for values. So application for types will use these square brackets here. And that's function quadruple, and it's again function double. We use it twice with different types instantiated here. So this will be just one function. You can apply it for every type x that you can come up with. So this is the ability of polymorphic functions. So this is polymorphism, theoretical polymorphism, like system F. System F allows you to do things like that. So we don't want to duplicate code as in lambda calculus, simply type lambda calculus. We can do it like this. All right. So the right name is parametric polymorphism. Parametric means that you can put any type there, value of any type, without any restrictions. So if you have some restriction, then it will be no parametric here. How to do that? Well, we extend simply type lambda calculus with this type abstraction and this type application. Also, we have one value type abstraction here. Well, because it's just another kind of lambda. No changes here. Again, gray background means what we changed from the previous type. So you want to abstract over values, you want to abstract over types. That's it. Yes?
How can values depend on types without types depending on types?
Technically, there is no depending types on types here.
But that's a type abstraction. That's a type
yes, but there are no tools for using this type in a way.
Right there. I'm confused. I'm sorry.
Well, you can write it, but there is no way to use it.
Oh, at the value
you cannot
level.
do it.
There's no way to use it at the value level.
Yes, you just use it for typing, and that's it.
I guess
so there is no depend. So there are no ways to do
I don't
this.
get the difference between system F and system F omega.
Well, we'll see it.
Oh, okay.
We'll see this difference.
So this is system F, though.
Yes, this is system F, exactly. All right, then types. For types, you have to extend this type variables for types here. And then this universal type. It's just extension to the type system here. So you remember, before we had only this type, but now we have type variables, and we have this quantifier here. So for all type x, we can do something. And also we can...
This is still just lambda 2?
Yes, lambda 2, yeah, exactly. So, and then also you can add these type variables in the context. See, without any additional information about it, just name. So we just put these names into the context. Then you should review your evaluation rules, but in fact there are no changes to evaluation rules. So you just evaluate as before without any changes at all. But surely you have to come up with new typing rules. And these are typing rules for this new kind of type application. And in fact, they are the same as before. But here's type application with square brackets, and this is type abstraction with big lambda. But they're just the same as in the case of type application and value application, value abstraction. By the way, if you introduce new kind of abstraction, new kind of application, but they share the same rules, then the question is it so valuable to come up with these new concepts? Maybe it's better to unify them somehow. Well, to say, well, it's the same thing if they have the same rules, and it takes about 10 years to come up with this idea, to unify them finally. And in current Haskell, we don't have different typing rules for types and for values. They're the same because, well, they are really the same. Other typing rules remain without any modifications, so just the same as before. But also you will need to introduce typing rules for big lambdas. Every big lambda will be type with this for all quantifiers here, and type application will use this substitution for types. So, but again they just repeat rules. So except for this type, new type, this is the same as before. And then the system has the same properties. It has progress and preservation. So it can be proved surely. It has normalization. So every term in system F is terminated. And that means basically that in Haskell we don't have system F, because Haskell is not terminated. Every term is not terminated.
Is there any system F language? ML?
Well, I think ML has non-termination too, but function. So we need some additional. We need some extensions to this language in order to get recursion. So this fix is something that allows us to to build non-terminated computations here. So some extension. It is also possible to erase types here, to erase and then evaluate. Unfortunately, it's impossible to do type reconstruction. So type reconstruction is when it goes way back. So if you have untyped lambda term in untyped lambda calculus, it's impossible to reconstruct types here. It's an unfortunate property of system F, so it's undecidable problem. That's why normally in programming languages you use some limited system F things. So, for example, sometimes you say, well, you cannot use for all for every type. You just limit set of types where you can use this for all. So if you come up in Haskell, they have such extensions like rank 2 polymorphism or rank n polymorphism. These are just trying to do something with these limitations. So the goal is to make type reconstruction or type inference decidable. So in general, it is undecidable. But if you limit system F somehow, then you can come up with a good algorithms for inferring types. So that's why you need this limitation. Yes?
Can you explain the difference between when you enable an extension like rank 2 or rank n and the explicit quantification that happens when you don't annotate things, but you know that, like, it can still parse things like identity function if you just write a to a f of x equals x. Like,
right.
You can still work with that, and you don't need to enable these extensions. So what is it really, the difference that you get from a polymorphism that doesn't come with?
You just come up with more expressive code. It is possible to write code more expressively.
But at
different
what point
types.
does that polymorphism break down and you would need to enable something like this ability to use these inference rules? So
these extensions, they allow you to use more sophisticated machinery for type system. When they were implemented, it wasn't so clear how to do that. So in Haskell, when they introduce some extension, they're not sure that it will work always. So they have some basic system which works, and we know that for sure. But then we introduce something new, and and it usually takes several years to understand that everything goes well. So that's why we have these extensions. And for some of the extensions, there was a situation, well, it was very good extension, but when in 3 or 5 years, we found some problems with it. Especially when several features try to be used together, they introduce some bugs which were not expected before. So that's why we need these extensions, and that's why it's not a good idea to just remove it and use it without any extension at all. Because technically it is possible to get some problems. So that's why we're doing that. Another thing which is very often discussed with these type systems is impredicativity. It's rather a thing with long-standing relation to the logic. I will not talk about that. So there are many sources on that if you are interested. But it's something to get around system F.
But
Yes.
I've seen this error message before that it's not. It says in the error message not yet. Like GHC does not have imperative types yet. So
Right.
presumably this is also.
Yeah. And I think we have this message for like 20 years or something.
Wait, I mean, aren't recursive data types predicative in a sense? No?
Well, it's not that. I think it's a little bit different thing. I think no. I think it's not that. All right. If you look.
On adding impredicative GHC by Simon Peyton Jones, but it's fairly new. But it's limited also.
But it's always useful to look several recent commits in the GHC code base just to follow them. All right. So how can we practice with system F? In the previous examples I've given you in that repository, I gave you some programs for working with untyped lambda calculus or simply typed lambda calculus. But when we are starting working with system F, we don't need that because we can use GHC compiler itself for practicing with it. So let's do that. So these are functions from system F, functions double, function quadruple. So with these types for all here, with big lambdas and all stuff like that, with this type application here. And in Haskell, we can write the same thing as follows. So that's exactly system F terms. I'm using this no inline pragmas because I want to get the same thing in GHC Core, just to show you that we'll have the same thing there. So in Haskell, we have no this for all here, although we can use some compiler flag to show this for all to us. But in general, it is just implicitly, it has this for all there implicitly. But we don't use it. So we can read it for all type A, just we use like this one. So this I like this quadruple. So it's much better than this in system F code. So this is not system F because there is no types here. But when you try to look at the GHC core that is generated from these functions, you will get something like this. So this is GHC core. I've got it with this flag dedump simple. And now let's try to find correspondence between that. Can you see type application here? Where is type application? There are no square brackets. Exactly. This add here is GHC core syntax for type applications. So it's exactly type application. And are there big lambdas here? Yeah, by the way, for all is here. This is for all. And it's explicit here.
It's there. A_A.
I think, yeah,
Function type A goes to A, is that creating a new type based on?
Well, I think so. This will be big lambda because it's big lambda for this type. So with at we specified it. So it's hidden here. So this is one lambda, but one argument is type level argument, and another argument is a value. So this is type. This is a value. So we just use lambda with 3 arguments, and technically that's 3 lambdas. One is big lambda, and then 2 others are small lambdas for values, for this one and for this one. And that's the body of this function. And again, here we have this big lambda for this type, and that's this body. And here we have 2 doubles. The first double is run with this type, and another double is with this type. So it's basically the same thing. These are system F terms, which were provided to us by the GHC compiler. So it's exactly the same. So if you want to work with it, then you can work with GHC compiler and to look at it. Then I think we have six minutes to go quickly with system F omega here. Remember that's another part of that lambda cube. So we want to have functions over types. For example, like this one, identity function over type. It takes some type and then it returns the same type as a result. In this system, we want to classify type somehow, and we'll need only one classifier, this asterisk or this star here. So I think the right name for it is Kleene star. It's logical name for. So Kleene, Stephen Kleene is one of the students of Alonso Church, actually. So we can also define functions like pair. Pair is a type with 2 arguments. Yes.
I don't think that's the Kleene star. No, the Kleene star is Bragilevsky. Yeah.
It's the same Kleene star, actually. I think. Well, maybe. But I think it's the same idea.
Okay, I just don't see.
Maybe. All right. So this is a function with 2 lambdas, 2 lambda abstractions. So we are building a type for pair. So if you have a pair and then you provide it with 2 types like pair, bool, not, then you get type of pairs of bools and nuts. And you can find out this kind for these pairs. So you should provide one type, another type, and then you get 3rd type here as a result. And also you have type application here. So this is exactly a pair of naturals and bools, 2 type application. So these are functions over types. And we can work with them using kinding instead of typing for values. In this system we have many kinds like this one. We also have kinding relation. It's like the same as typing relation, but it works for classifying types. There is also definitional equality. It's equality for types like this one. If you have identity function over types, then these 2 types, they should be equal. Well, because ID not is evaluated as not, he's as bool, so it will be not to bool. So you want to have system where with this equality of types. And then there is parallel reduction. Is just we use this equality, but it goes from this side to that one. So it's directed variant of it. So it's actually quite a big system. I don't want to talk a lot about it. We have many rules, because we have many notions here. These are rules for computing kinds, like for big lambdas. All of them, they look like the corresponding rules, typing rules. But these are kinding rules. Some rules for equalities and something like that. So just, I don't want you to follow them, to think about them, but we have them in this system. Then we also have to modify typing rules somehow. It doesn't matter how we do that. So, but we have many things because, yeah, we have different parts on top of this fraction, and we use something with equality. So there are many things that should be done in this system for that. And I'd like to finish with the following. This is the way that we've done up to this point in this workshop. We're talking about untyped lambda calculus, and then it extended somehow to the system F omega with type functions, with values, polymorphic functions, and that's it. And this is another quote from GHC commentary, which says that for a long time, for many years, it's like 20 years, this system F omega was exactly the system behind GHC Core. Apart from algebraic data types, and after the break, we'll see how they use those algebraic data types. But then they started to extend it with different, with other constructions. So the last part of this workshop will be exactly about these extensions. So we have this system F omega in the GHC Core, and then we'll follow several extensions. Not all of the extensions, I just picked several, the most interesting extensions, and I will talk about them. So the last section of this workshop will be as follows. We will look at extensions to the Haskell language. Then we'll look how it can be translated into GHC Core, and how it is necessary to extend GHC Core to be able to do these translations. So we'll look at these coercions and equality constraints. Then we'll look at type level computations like type families and stuff like that, how we can work with it in the GHC Core. I think I will not have time to talk a lot about dependent type system. Well, it's not implemented yet, but there is work in progress. But that is our final goal, to reach this point where we can extend our Haskell with dependent types. So I think that's enough for this section. Thank you very much here. I think it's half an hour break, and then we'll continue with the last part of this workshop.